This lesson covers solving trigonometric equations. When you're solving trigonometric equations, you want to see what values make the equation true. And then you should always get in the habit of checking your solutions. In trigonometric equations, since the domain of sine and cosine are all real numbers and it keeps going, there are infinitely many solutions. So for this class, we're just going to go ahead and find all the solutions that you would normally see on your pi plate. So all the solutions between 0 and 2 pi, including 0 but not 2 pi. Okay, the first example I'm going to do, I use a technique called collecting terms. And the reason I can use it on this problem is I see that I've only got a sine x here and a sine x there. I don't have any other terms. It's very basic and simple. So I'm going to collect all sine x on the left-hand side. So I added sine x to both sides. Then I went ahead and isolated sine x. So I subtracted the square root of 2 and I divided by a 2. What that gives me is sine x is equal to negative square root of 2 over 2. And then I want to find all the angles that have a sine of negative square root of 2 over 2. I know that these are all the pi over 4 multiples, and since it's negative, it has to be in the third and fourth quadrant. So that's how my answers got to be 5 pi over 4 and 7 pi over 4. And then I always check my work with a calculator. I would plug 5 pi over 4 in for x here and check to see if it's true, and I would plug 7 pi over 4 in for x here and see if it's true. Okay, my next example is the technique of factoring GCF. So in factoring GCF, the reason I'm using that technique on this problem is you notice that I have a sine theta times tangent theta minus sine theta. So I have two different trigonometric functions here. And sine theta is in both these terms, so I'm going to factor out the greatest common factor, which is the sine theta. And once I factor out sine theta, I'm left with tangent theta minus 1. I've noticed more and more lately, students are not putting parentheses around terms that are multiplied. So this is very important. Be careful that you do make sure you use the parentheses here. Once you factor, you set each factor equal to 0. So sine theta equals 0 and tangent theta minus 1 equals 0. Sine theta equals 0 when theta is equal to 0 in pi. Solving this for tangent theta equal 1. Tangent theta equals 1 when theta is going to be pi over 4 and 5 pi over 4. So my angles for the solution are all those 0, pi over 4, pi, and 5 pi over 4. All of those would work. The next two examples, one is going to be factoring a quadratic. In factoring a quadratic, what I'm going to see is in this case I've got 2 sine squared theta minus sine theta minus 1 equals 0. It's in quadratic form because I have a sine squared. So if you think of it this way, if I let x equal sine theta and I rewrite this, I would have 2x squared minus x minus 1 equals 0. I can factor that. And there's different ways that you've been taught factoring. I'm just going to go ahead and have it in factored form. So the first factor would be 2x plus 1, and the second factor would be x minus 1. And this is equal to 0. You cannot factor something unless it equals 0. You can't solve an equation. Then I'm going to go ahead and rewrite this equation, but instead of having x in there, I'm going to put sine back in there. So 2 sine theta plus 1 is the first factor. Sine theta minus 1 is the second factor, and they equal 0. Set the first factor equal to 0 and solve for sine. I get sine theta equals negative 1/2. Once again, this is in the third and fourth quadrant, so theta is going to be equal to 7 pi over 6 and 11 pi over 6. The second factor gives me sine theta equals 1. Sine theta equals 1 when theta is pi over 2. So my solutions are 7 pi over 6, 11 pi over 6, and pi over 2. The next example I have is I'm going to be using an identity. Just trying to get this to focus. So this case here, I have sine squared x equals 3 cosine squared x. I can't factor it even though I have sine and cosine. So I'm going to use an identity on this one, and there's several different ways you can do this. You could use Pythagorean identity and replace sine squared with 1 minus cosine squared. You could still use Pythagorean identity and replace cosine squared with 1 minus sine squared. In this case, I'm showing you how to divide by cosine squared x. Subtracting 3 cosine squared x with this technique is not going to help me. When I divide by cosine squared x, I get sine squared x over cosine squared x equals 3. Now I can use the quotient identity. Sine squared over cosine squared is going to be tangent squared. So I replace sine squared x over cosine squared x with tangent squared x, and that equals 3. I take the square root of both sides, and I get tangent x is equal to plus and minus the square root of 3. It's important to remember the positive and the negative. If you're solving for something squared, positive answers will work and negative answers will work. And you want to make sure that you have all of them. Tangent x is equal to the square root of 3 at all the pi over 3. So since there's plus or minus, my answers are going to be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. I have 2 more examples. These are a little bit longer examples because they take a little bit more to understand. Some students struggle with these. I've had other students find the patterns, and I'll explain the patterns that they have found to help you. So in this case, I have tangent 2x equals negative square root of 3. Right now I'm going to leave the 2x. So I know that the angle 2x is going to equal 5 pi over 6 and 11 pi over 6. Since this is negative square root of 3, it's going to be in the second quadrant, which is 5 pi over 6, and the fourth quadrant, which is 11 pi over 6. But I don't want to solve for 2x, I want to solve for x. So if I divide both sides by 2, 5 pi divided by 6 divided by 2 gives me 5 pi over 12. 11 pi over 6 divided by 2 gives me 11 pi over 12. These answers are only between 0 and pi. 12 pi over 12 would give me pi. So we need another set of answers that are coterminal to 5 pi over 6 and 11 pi over 6. So if 2x equals 5 pi over 6, coterminal to 5 pi over 6 is going to be 17 pi over 6. Coterminal to 11 pi over 6 is going to be 23 pi over 6. So if I take 17 pi over 6 and divide it by 2, I get x is equal to 17 pi over 12. If I take 23 pi over 6 divide by 2, I get 23 pi over 12. So my answers are going to be all 4. 5 pi over 12, 11 pi over 12, 17 pi over 12, and 23 pi over 12. So one of my students several years ago said, oh, I see the pattern. I have 2x equals these 2 answers. This 2 in front means I need 2 more. I need 2 sets of them. So this is the first set. This was the second set. They discovered if they have a 3 here, they would need 3 sets of answers. They have a 4x. They would have 4 sets of answers. So that's how they knew to keep going. So in the next example, I'll show you how to keep going. So this next example, I have 10 sine 3x minus 2 equals 8 sine 3x minus 1. This one's a little bit more work, but I only have sine. I don't have anything else. So I'm going to collect all my like terms. I subtracted 8 sine x, and I added 2. And I got 2 sine 3x equals 1. So sine 3x equals 1/2. Remember, this is 3x, but I still want to find what 3x equals, what angles. So sine is positive in the first and second quadrant. So I get pi over 6 and 5 pi over 6. But this 3 tells me I want 3 sets of answers. So this is the first set. Coterminal to pi over 6 is 13 pi over 6. Coterminal to 5 pi over 6 is 17 pi over 6. That's my second set. Now I need to find my third set. Coterminal to 13 pi over 6 is 25 pi over 6. Coterminal to 17 pi over 6 is 29 pi over 6. I know that these last four answers are greater than 2 pi. But that's not my final answer. Once I divide by 3, pi over 18, 5 pi over 18. First set. 13 pi over 18, 17 pi over 18. Second set. 25 pi over 18 and 29 pi over 18. There's my third set. So these are all my solutions between 0 and 2 pi. 2 pi goes up to 36 pi over 18. So this one is below that. So those are all my solutions.